Hello and welcome to the Callum Cymru revision sessions for 2024. My name is Matthew McMillan. I am a teacher at Christ College in Brecon as well as an A-level maths examiner. There are 4 sessions that I did last year and you might want to go and review those. This year I will be doing another 4 sessions, and today's session we will be looking at the roots of a polynomial. Okay, so in front of us is the section of the specification relating to the roots of a polynomial. They require us to know about the roots of a polynomial up to a quartic equation, although there is a pattern that you can follow for anything higher. I think in today's session I've mainly concentrated on cubic equations, but you can use similar results for quartic equations. We might also have to look at what happens if we transform the roots. Or if we take a combination of the roots and sort of stick them together in an odd way. Now, we will also look at a question involving a geometric progression, and I'll also just talk a little bit about an arithmetic progression. Okay, so we have on the screen the general rules for the roots of a polynomial. In class, your teacher should have shown you how we come about these, and you kind of just want to learn the pattern. We only need to know up to the quartic, but you're spotting things such as it goes negative, positive, negative, positive, and then just remembering it's b over a, c over a, d over a, and then whatever the last thing is over a. Very often, but not always, they're usually quite kind with whatever the a value is, so that would be this number here. Often that is a 1, but not always. Okay, so this might be a typical question using the roots of a polynomial. We have a cubic here, so I've just for reference written the sort of cheat sheet rules that we can use to help us when we're dealing with our roots. The other thing to spot is this question involves a geometric progression. They do expect you to know what a geometric progression is and an arithmetic progression. An arithmetic progression goes up by the same amount each time. It has a constant difference. A geometric progression goes up by a common ratio. So we would start with a value such as r, and then we would times that by a common ratio r, and then we would times it by a common ratio r again, so we get ar squared, and then you get ar cubed, etc. Basically, it's a series of numbers where you multiply to get to the next number. So that's a geometric progression. That means that our roots here, so roots are alpha for the first one, and then the next one is going to be alpha times the common ratio, and then the next one is going to be alpha times the common ratio squared. They would like to see that explicitly for the mark. The other thing that I want to just keep an eye on is what each of the values are. So a is 1, b is f, c is g, and d is h. So we'll start with the sum of the roots, alpha plus beta plus gamma. In this instance though, we're not using alpha, beta and gamma, we're using alpha plus alpha times the common ratio plus alpha times the common ratio squared, and that equals negative f over 1. So I'm using this rule up here. Let's tidy this up a little bit. Maybe looking at this bit here, it looks like we could factorise out the alpha. So we'd get alpha and then 1 plus r squared equals f minus f. Let's do the same for the sum of alpha beta. So we're going to get alpha times alpha r plus alpha times alpha r squared plus alpha r times alpha r squared, and that should equal, where are we? We're looking here, so it's g over a, which is 1. Let's see if we can factorise anything out of this. It looks like each thing here is going to have an a times an a, so I think I can factorise out an a squared. Each thing is also going to have an r, so I'm going to factorise out an r. That leaves me with, well, from this bit here I'm going to get a 1. From this next bit here, what are we getting? We're going to get another r. And then from the next bit here, I'm going to be left with an r squared. And that equals g. Let's take these two equations and let's divide one by the other. So equation 2 divided by equation 1, and let's see what we get. So alpha squared r 1 plus r squared divided by alpha 1 plus r squared equals, and we've got g over minus f. I guess these two bits here will cancel, and also the alpha squared on the top and the alpha on the bottom, that's going to cancel. So we're going to ending up here with alpha r equals negative g over f. The final thing I haven't considered is product of the roots, so I'll just have a think about that over here. Alpha, beta, gamma. What do we have? Alpha times alpha r times alpha r squared, and that should equal h over 1 minus h over 1, sorry. So this gives us, well, I guess it's alpha r all cubed equals negative h. I think we're nearly there. What might be helpful is if we take this bit here and if I cube it, so alpha r cubed, that gives us negative g over f cubed. And then I think it's a case of making these two bits equal to each other. So we get negative g cubed over f cubed equals negative h. I guess because there's a negative on both sides, we can kind of cancel the negative out. And what are we trying to get it to look like? We're trying to get it to look like this. So g cubed equals f cubed h. Okay, so that's covered a little bit of work on roots and coefficients, this part here. We've also had a little look at a geometric progression and an arithmetic progression. The geometric progression then, just to remind you, that's where you start with a term and then you multiply it by a common ratio, and that was in that question. Arithmetic progression, that's where we might start with a term and then we add a common difference each time, such as this. And you need to know both of those terms. Okay, so we have another question involving a cubic, and this time they're taking the roots and they're just doing something a little bit weird with it, and we're kind of relying on our algebra skills to work out what's going on here. I'll start the question again by sort of making a note of what each of these things are. So A is 1, B is negative 2, C is 2, and d is 1. And I might also make a little note of what the sum of the roots are. So that should be 2. What the sum of alpha beta components are, that should be 2 as well. And then the product of the roots, and that should be -1. So I'm just using the rules that are at the top of the page. And then I'm having a look at the question. So question A, show that, and then they've done some manipulation of the roots and show that it equals -8. So I'll kind of take what they've written, beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma, and I'll have a think about, I don't want to just make it equal -8, maybe I'll think about how I can combine this all as a single fraction. So I want to make the denominators the same. If I times this first one by beta gamma, that then means that I need to multiply the top by beta gamma, so effectively I'm going to get beta gamma squared. This next one I'm going to multiply by alpha gamma, which means I'm going to get alpha gamma squared, and this one I'm going to multiply by alpha beta, which means I'll get alpha beta squared. So I now have a common denominator. Let's write this a little bit more clearly, and I prefer to see it in this order: alpha beta squared plus alpha gamma squared plus beta gamma squared all over alpha beta gamma. Now I'm looking at that bottom bit just here, the denominator, and that's looking pretty good because we've already got that information given to us. This top bit though, I don't have that given to me, so I'm going to need to do a little bit of work to work out what's going on there. Now because I want to get alpha beta squared, alpha gamma squared, beta gamma squared, I want all the bits squared, what I do is I just take alpha beta plus alpha gamma plus beta gamma and I square it. That introduces the alpha beta squared, the alpha gamma squared, and the beta gamma squared. Unfortunately, it gives me a load of stuff that I don't want. If I tidy this up a bit, there we go. I've still got my 3 things that I do want, because these are the numerator. And what I've done is I've just kind of factorized each of the components, because I can see I've got 1, 2 components here that are the same. And again, I've got 1, 2 components here, and then 1, 2 components there. So I've got 2 of everything. All of them have an alpha beta gamma in, and then I'm just sort of looking at what's left. The bit that's left is the, well, we've got a single alpha that's left, a single beta that's left, and then a single gamma that's left. If I rearrange this now, because I want to get this bit coming out, I just move the 2 alpha beta gamma bit over to the other side, and now I've created an expression for alpha beta squared, alpha gamma squared, and beta gamma squared. My aim, if you like, is to take these bits here and try and get these bits here. So you can see I've got that bit now. I've got alpha beta gamma, so I've got that bit there, and I've got alpha plus beta plus gamma. Well, that's good now, because those are numbers that I can work with. So we will put this in. So this numerator now, I can rewrite it as alpha beta plus alpha gamma plus beta gamma all squared minus 2 alpha beta gamma times alpha plus beta plus gamma. And we've still got the denominator alpha beta gamma. Now we can put some numbers in. So the sum of the alpha beta bits is 2. So we've got 2 squared, take away 2 times alpha beta gamma. So if I look at my top here, alpha beta gamma is -1, times the sum of the roots alpha plus beta plus gamma, so that's 2, divided by alpha beta gamma divided by -1. So this equals 4 take away -4 all divided by -1, which equals -8, which is what they've asked for. Okay, moving on to part B. Looking at part A, I can see that the sum of these roots, these are the new roots of a new equation, the sum of the roots is given. It's -8, it's from part A. So I know, just looking up here, what does the sum of roots equal? It equals -b over A. So -b over A must equal -8, and that's from part A. It gives us that. The other thing that's quite easy to find is the product of the roots. So I'm going to multiply each of these things together. So we've got beta gamma over alpha times gamma alpha over beta times alpha beta over gamma. I can see there's going to be a certain amount of cancelling out going on here, so I guess the gamma here might cancel with one of the gammas here, the beta here could cancel with that beta, this alpha here could cancel with that alpha here. So what are we ending up with here? Well, it looks like it's alpha, beta, gamma. Well, alpha, beta, gamma is up here. And it's still using the same alpha, beta and gamma as before, so we know that this equals -1, and the sum of our roots, the product of our roots is -d over A. So those two bits are quite straightforward. It's the next bit that's a little bit tricky. I want to find, because I've done this bit here, I've done this bit here, I want to find the sum of the alpha beta components, so I'm going to have to do a little bit of work multiplying different components together here. So I have done alpha beta over gamma times alpha gamma over beta, and I'm kind of pairing these things up 2 at a time, and I should get 3 different pairings. Plus, and we'll just keep going, alpha beta over gamma times, and I think I've done this one, so I need to pair it now with this one, beta gamma over alpha, plus, and then the last thing to pair together is beta gamma over alpha times alpha gamma over beta. It looks pretty complicated, but I think there's going to be a load of cancelling here, because I think here I've got a beta and a gamma and a gamma. Oh, that's not a gamma, that's an alpha. A gamma and a gamma. I think that's going to leave me with alpha squared. Here we can cancel the alphas and the gammas, so we're left with beta squared. And then on the last one, what have we got? Alpha and alpha, beta and beta, so we're left with gamma squared. It's looking quite good, except we don't have an expression for alpha squared plus beta squared plus gamma squared. We've got an expression for alpha plus beta plus gamma, this one here. What I need to do then is I need to use a similar method to what I've done up here. If I take this kind of situation, say alpha plus beta plus gamma, and square it, I should get something similar popping out. This is one that you can just go away and learn because it pops up quite often. If we do this, this is what we get coming out: alpha plus beta plus gamma squared, you can see it's a very similar situation to this, minus 2 times, and then we've just got the sum of alpha beta, which is a bit like this, but slightly different. So do we have numbers for this? Well, we have got the sum of alpha, beta and gamma, that's 2. So we've got 2 squared, take away 2 times, and then the sum of alpha, beta is 2, again from the top. This gives us 0. And that is this middle bit here. So that is what C over A is. Now, we can choose any value for A. So if A is 1, then we get B equals 8, C equals 0, and D equals 1. This implies that our equation is 1x cubed plus 8x squared plus 1 equals 0, because the C component is 0. Let's take a look at what this looks like on Desmos and how changing the value of A would affect things. Okay, so we have the situation set up here on Desmos, and we've got the equation that we've just found, x cubed plus 8x squared plus 1. You can see I've set A as a value of 1. If I change the value of A, it will affect the coefficient of x cubed. It will also affect the coefficient of x squared and x and the constant. So just take a look at the graph as I change the value of A. It does change the shape of the graph, so it's stretching it. However, the key point is that the root down here, that does remain the same. So that's what we're using, is the fact that the root will stay the same, and we're not really worried about the changing of the graph. So I guess you could say there's a whole family of solutions here, but usually you just set A equals 1. Okay, so the final thing we'll look at is transformation of the roots of a polynomial. So we have a question here, we have a polynomial and it tells us that we've got some roots. Then find the equation of a polynomial with some transformed roots. They seem to have doubled the value of each of the roots. If we just kind of take each of these values, so A is 1, B is negative 2, C is 3, and D is negative 4. And I just want to note down somewhere what the original sum and product of all the roots are. So alpha plus beta plus gamma, that's going to be 2. The sum of alpha beta, that's going to be 3. And then alpha beta gamma, that's going to be 4. And we've got a couple of ways of dealing with this. So the first method is to think about, well, what about the sum of these new roots, 2 alpha plus 2 beta plus 2 gamma? Well, that is 2 lots of alpha plus beta plus gamma. And we already have alpha plus beta plus gamma, so it's 2 lots of 2, which is 4. We'll do the same for the sum of alpha beta parts, but this time it's 2 alpha times 2 beta, add 2 alpha times 2 gamma, add 2 beta times 2 gamma. Well, I can sort of see here I'm going to get 4, because each one has a 2 times 2 in it, and then from the first bit is alpha beta, from the next bit is alpha gamma, and then the next bit is beta gamma. So that is 4 times the sum of alpha beta and the sum of alpha beta is 3. So we don't know that that bit is 12. And then the final bit is the product. So 2 alpha, 2 beta, 2 gamma. That equals 8 alpha beta gamma. And we have got alpha beta gamma as 4, so it's 8 times 4, which is 32. That then gives us our new equation. And if we set a as 1, then we get x cubed minus 4x squared plus 12x minus 32 equals 0, and that's using the rules at the top of the page. We could use a different letter here because I guess we've created a different polynomial, but it doesn't really matter. The alternative is we will basically say that each of the values in here, each of the roots are going to be double, so we want to use a substitution. Use a letter such as w equals 2x, and then that implies that x is w over 2, and in our equation we're going to substitute in w over 2. So instead of x cubed, it's now w over 2 cubed. Instead of minus 2x squared, it's minus 2 w over 2 squared. Instead of plus 3x, it's plus 3 w over 2, and then minus 4. So if we cube this, we get w over 8, or w cubed over 8. Here we're getting 2 squared would be 4 as the denominator, but we're timesing it by 2, so we're going to get minus w squared over 2. Here we're going to get plus 3w over 2, and then we've got minus 4. They haven't, or I haven't been explicit in the question, but usually want an integer coefficient. So I'm going to times everything here by 8, and that gives us w cubed minus 4w squared plus 12w minus 32. And obviously it's the same as the previous answer, which it should be. So that's how you could deal with a transformation of a root. The other type of question that you might get, instead of a multiplying of the roots, you might get something like alpha plus a number such as 3, and then beta plus a number, gamma plus a number. That's the other type of question you might get. Again, you could investigate what would happen here and use this method, and hopefully what you're aiming for is you're aiming to get these things coming out that you can just go ahead and use. Okay, so taking a look on Desmos, on the right hand side of the screen here, I've got the original cubic function plotted, and you can see there's a root at 1.651, and if I just overlay the new transformed function, that root that was at 1.651, well, it's doubled to 3.301. Now on Desmos it struggles to show the complex roots as well, so on the left hand side here, do you see where the circle is here? That's showing the original root of 1.651, and then the two roots at the top and the bottom, those are showing where the complex roots would lie. That's of the original function. When we take our transformed function, which is this visualization here, the sort of roots have all basically stretched, they've all doubled in size. So that's kind of showing what's happening to the roots, they're all doubling. Okay, just to end then, we're going to have a look at the number of roots, or the number of real roots of an equation, because that is quite a common question. So we've got an equation given to us, and it tells us that the roots of the equation are given by alpha, beta, gamma. Find the cubic equation whose roots are, and then it's some kind of amalgamation of all those roots. Now, because we've done a question very similar to that, I'm not going to go through that question. You might like to pause the video and just try that part yourself, part A. The mark scheme, here we go. It's worth just noting that you get a mark for just writing the sum of the roots, the sum of the alpha beta components, and then the product of the roots. That's 1 mark. And we get the required equation. Really, it's part B that I'm interested in. And it's probably just worth homing in on this bit here. Okay, so the alpha squared plus beta squared plus gamma squared, that's quite a common thing to ask. We can go ahead and derive that in the middle of the exam, and I've shown you methods for doing that in previous slides. Or you might just want to try and remember, this is kind of like a cheat sheet for, well, we've got the cubic one, it's just at the bottom here. There you go. Alpha squared plus beta squared plus gamma squared, and it tells you what you'd need to do. This bit here is the sum of the alpha beta components. It gives you the quadratic one and the quartic one. These things you are kind of expected to either know or just be able to derive. So the reciprocals at the top, we need to know them. The products of powers, sums of squares, and the sums of cubes. Decide yourself whether you want to memorize them or derive them. Okay, so for part B, I've copied across the part of the cheat sheet that I wanted, and we want to show that the sum of the squares of the roots will equal 0. So alpha squared plus beta squared plus gamma squared equals 0. From before, I had worked out that alpha plus beta plus gamma equals -2. The sum of the alpha beta components 2, and then the product of alpha beta gamma is -3. I'm going to need them. So in fact, I'm just going to rub this out, I don't want that 0. Let's copy down what we've got here. So we've got alpha plus beta plus gamma squared minus 2 times the sum of the alpha beta components. So this is going to give us, well, if we look at the top, we've got -2 squared, take away 2 times the sum of the alpha beta bits, so 2. So that is 4 minus 4, which equals 0. That's quite convincing. Now, if we look at this here, because we've done the show that bit, deduce the number of real roots of the cubic equation. I guess if we had alpha squared plus beta squared plus gamma squared, and we got a number that was greater than 0, then we could have a situation that looks like this on a graph, where we've got 1, 2, 3 real roots, or we could have a situation that looks like this. That's not very well drawn, but we've got 1 root there and then a repeated root there, so that's 3 roots. That's 3 roots. Or we could have a situation like this, where we've just got 1 root. If though alpha squared plus beta squared plus gamma squared is less than or equal to 0, to make that happen, because we're squaring numbers here, we would have to have at least one of these having some kind of complex element to it. Or an imaginary part, otherwise we're going to get something always greater than 0, and if we're getting something equal to 0 or less than 0, one or more of these must have an imaginary part. Now, because of the shape of a cubic graph, we are not going to be able to get one that looks like this, and we are not going to be able to get one that looks like this. We will only get one that looks like this. So if we have this situation, we will say that there is one real root. So our answer here, when it's asking about how many real roots there are, we will say there's 1 real root, and then we need to make a comment so that we show that we understand what a cubic is. Cubics have 1 or 3 real roots, So that's kind of established that fact. As the sum of the squares, so as alpha squared plus beta squared plus gamma squared equals 0, not all the roots are real. So that's kind of explained why we only have one real root. Okay, so I think we've covered everything on the roots of a polynomial section of the specification. We've looked at the relationship between the roots and the coefficients. We've had a look at situations where the roots are a transformation or some kind of combination. We've thought about arithmetic and geometric progressions. And we've also had a look at in what situations, how many roots we would get in certain situations. Okay, so that's completed our session on the roots of a polynomial. Next week I'll be looking at some proof by induction questions, and then we'll have a look at momentum and impulse in session 3, some mechanics work, and we'll also review, in session 4 we'll do a review as well as look at Hooke's law. Session 4 will be a live session, so if you have any questions, bring them to that session.